So I think now we are ready to speak about compact operators. So now let X and Y be normed spaces because we need the vector space structure in order to define linear operators, and we need the norm structure in order to have a metric. And we say that a linear operator between such spaces X and Y is called compact if it maps bounded sets in X to, and now here's the thing, relatively compact sets in Y. So recalling our lemma 2, we have that relatively compact sets are bounded. And recalling lemma 3, we have that in finite dimensional setting also the other direction holds. So relatively compact sets are bounded sets, and that implication is always true. And the reverse direction holds by lemma 3 if the sets that we're talking about are contained in a finite dimensional setting. Maybe it's easier to understand that setting if we draw a little diagram here. So if we start with a bounded set let me say S in X, then the image of that set under the map A over here is the set that we're discussing here. So this has to be a relatively compact set, and we're discussing when this is equal to being a bounded set, is equivalent to being a bounded set. Well, just like A of S is the image of S under the map A, we can look at the image of the whole space X under the map A, which is of course what we call the image of the operator A. So it's a subspace of Y, and it contains our set A of S, which is the one we're discussing. So if that image is a finite dimensional space, then we can indeed go this arrow backwards. Okay, but if we replace the words relatively compact here by bounded, as we just discussed, then we arrive exactly at the definition of a bounded linear operators. Okay, let's just summarize this. So between the statements that A is a compact operator and A is a bounded operator, we always have this implication, and we sometimes have the reverse implication, and more exactly sometimes means if the dimension of the image space of A is finite. Okay, that's quite an important insight. Let's frame that so we can easily find it later on when we need this statement. The discussion of the dimension of the image space leads us to our next definition. Instead of dimension of image of A, let us further on just say the rank of A. And I'm sure you remember that fact from linear algebra for finite matrices, the rank of your matrix is just the number of pivots, which happens to be the dimension of the image of your matrix or operator. And now that we are at it, let's write f of x, y for the set of all bounded operators from x to y with a finite rank. So f is abbreviation for finite rank, and we call these operators finite rank operators. And to also have a notation for the set of all compact operators, let us write k of x, y for the set of all compact operators from x to y. At this case, we do not have to say bounded, because we know that compact implies bounded, and that is always the case. So just for completeness, let's write the name down again, compact operators. Okay, again, just like in the case of Lxy, we will abbreviate fxx by just f of x. So if y is the same as x, then there's no need to write it again. And the same with k. Okay, so now we have three classes of operators. We have bounded linear operators, compact operators, and finite rank operators. We know that every compact operator is a bounded operator, and we know that every finite rank operator is a compact operator because it has finite rank and is bounded. That's exactly this definition. It's bounded and has finite rank. So if we summarize this, we could just draw the following diagram. So the largest set is the set Lxy of all bounded operators from x to y. This contains the set Kxy of all compact operators from x to y. And that again contains the set Fxy of all finite rank operators. And this is a really important point here, because if you remember that somehow the aim of this course is to solve infinite dimensional problems like ax equals b with, well, complicated, certainly infinite matrices A. So let me say these correspond to bounded operators out here, and to replace them by simpler, because somehow finite dimensional problems, an xn equals bn. Okay, and if we say that we can represent an on a computer, we can completely store it on a computer, then it must somehow be given by a finite matrix. So it's got to be a finite rank operator. So our sequence of ANs is sitting in here and is trying to somehow approximate an operator A that is out there. And we have to understand what kind of approximation is appropriate here in order to make this possible. And a very important statement in this context is the following lemma. Lemma 4 says that Kxy is a closed subset of Lxy. Do you remember what closed means? It means if you have a sequence of compact operators and that sequence converges in the sense of Lxy, so it converges in the operator norm, then the limit will again or still be inside of the set of compact operators. Or to phrase it differently, if you want to have convergence in the operator norm, like this, and your sequence of ANs is compact, which it is if it's finite rank even, then your limit A will again be compact. So what I'm saying is that using this operator norm convergence, you cannot cross this boundary. Let us not prove lemma 4 here, but let's instead state two other lemmas that will indicate why we might want to cross the green boundary. Lemma 5 is a very important statement about compact operators, and it says that if you have two bounded operators and a compact operator, and if these operators are such that you can form the compositions A T and T B, so for example T maps from a first space into a second space, and then A maps from that second space into a third space, while with B it's just the other way around, then the statement is as follows: both of these products are compact. So whenever a compact operator meets a bounded operator, no matter if from the right or from the left, then the product will be compact. The proof of this fact is not too difficult. Let's start with the product TB. And to show that this is a compact operator, let's apply it to some bounded set. Okay, now remember that these compositions here, you have to read from the right to the left. So first you apply the operator B to that bounded set, but because B is a bounded operator, the result will be bounded. And then to that result you will apply your operator T, but because that operator is compact, it will map any bounded set to a relatively compact set. So in total, this composition of B followed by T maps bounded sets into relatively compact sets, and therefore is a compact operator. Okay, let's try and do the same test for the other operator that we claim to be compact. Now this is AT, which is T followed by A. So again, start with a bounded set, and this time we apply the compact operator T first, giving us a relatively compact set, and only then comes our bounded operator A, and what we have to show is that the result will again be a relatively compact set. Okay, so for this proof it remains to be shown that a bounded operator A maps relatively compact sets into relatively compact sets, and as soon as we've done that, we have finished our proof. Well, let's put this down to our list of questions that, if you want, we can address in the exercise session. So in this lemma 5 you can see that the property of being a compact operator is very strong. It somehow dominates the product of compact and bounded operators. So the product of a compact and bounded operator is always compact, which maybe reminds you of like the product of a null sequence and a bounded sequence is always a null sequence. or the product of an even number by any other number is always an even number. So this is something that dominates multiplication, where in this operator setting multiplication means composition. Okay, and now finally here's lemma 6 on compact operators. Compact operators, let's say t, like we did before, from x to y, are never invertible unless we are in the finite dimensional setting, in which case dimension of x and dimension of y have to be the same in order to guarantee you an invertible operator between x and y. But if that's not the case, then a compact operator can never be invertible. So in particular, as soon as one of the spaces x or y is infinite dimensional, and you have a compact operator between x and y, then that one cannot be invertible. Okay, the proof is surprisingly simple. So let T be compact from x to y, and suppose, contrarily to what we claim, that the inverse exists. And because T being compact is always a bounded linear operator, that inverse T inverse would at least be a bounded linear operator, now of course in the reverse order from y into x. But then we can compose the two operators T and T inverse in whatever order and get, in one case, the identity operator on y, and in the other case the identity operator on x. And because here we are composing a compact operator by a bounded operator, both of these products will be compact operators by the previous lemma 5. But if the identity operator is a compact operator, then that means it maps any bounded set into a relatively compact set. So for example, the unit ball, which is a bounded set, is mapped onto itself because it's the identity operator, and then that itself would have to be a relatively compact set. So this means that every bounded set, for example the unit ball in Y, is a relatively compact set, and by our lemma 3, this is happening if and only if your space, in this case Y, is finite dimensional. So this here implies that the dimension of Y is finite, and in the same style, this here implies that the dimension of X is finite. So T would be an operator between two finite dimensional spaces. Okay, and from our basic linear algebra course, we know that there's only a chance for T to be invertible if the two dimensions agree, if they are equal. Okay, and that's exactly what our lemma is saying. So what have we just learned if we take all of this together? Well, in the last lemma, we have learned that the invertible operators, like the A we care about, are outside the compact operators. So the invertible operators are disjoint from the compact ones, maybe here. And on the other hand, the operators that we can store on a computer are certainly finite rank operators, and that these finite rank operators are always compact operators. But on the downside, that using the convergence by operator norm, we cannot cross this green boundary. So using our finite rank operators and operator norm convergence, we will never be able to reach an invertible operator out here, because this boundary cannot be penetrated by operator norm convergence. So this is showing that in our goal to approximate the solution X by solutions of these simpler problems, we are trying to approximate A by finite matrices and B by some simpler right-hand sides. We can probably not use this kind of convergence down here for the operator side, because like I said before, A up here will be invertible, whereas the ANs down here will be finite rank, and then that's just impossible by our lemma 4, which is saying we cannot cross the green border. Okay, we will worry about this problem another time, I think next week, and we will see by what other kind of convergence we could replace that one in order to solve the problem.